Okay. Uh, good evening to everyone in India, and good morning to the people.
Okay, this
Hello. Is this Atul? No.
yeah, some issue. Hang on.
It says live streaming.
Okay, go.
Okay, welcome to all to this next edition of next talk in the series topics in special functions and number theory. It's my pleasure to introduce Sudhir Pujahari of NISER Bhubaneswar. And he's going to speak about the moments of the trace of Frobenius in arithmetic progressions. Thank you, Sudhir. Go ahead, please.
Yeah, thank you, Krishnan, for the invitation. And also, so the plan of today's talk are as follow. In the first part of the talk, I'll be introducing what is known as the theory of equidistribution briefly, as I have been told that this talk is mainly for graduate student. So this is most of a self content talk, except few at the end, few part of the talk. In the second part of the talk, I will introduce something known as set-rotate conjecture, a brief introduction to set-rotate conjecture and recent development. And finally, we'll see distribution of moments of trace of Frobenius in arithmetic progression. In particular, we'll see a set-rotate law for the trace of Frobenius in arithmetic progression. And today's content of the talk is joint work with Benken and Catherine Brinkman. Benken is in the University of Hong Kong. Catherine Brinkman is in the University of Cologne. But to start with, let us start with a question that let us look at the sequence n theta, where theta is an irrational number. And whenever we see curly bracket in today's talk, we are talking about fractional part of the sequence. So for example, if it is 2.3, we will look at only at 0.3. If it is 7.4, we will look at only 0.4. So this is what this curly bracket means, the fractional part of the integral. And in 1842, Dirichlet showed that if you look at this sequence n theta, where theta is an irrational number, and if you look at the fractional part of the theta, then 0 is going to be a limit point of this sequence. In other words, any neighborhood of 0 will contain more points of this sequence n theta. Couple of years later, Kronecker showed that the sequence n theta, not only 0 is going to be a limit point, but any point of the unit interval is going to be a limit point of the sequence n theta. In other words, the sequence is dense in the unit interval. And later on, 1909 and 1910, Bogle, Ramanujan, and Sierpinski, they asked the question that how the sequence n theta is distributed in the unit interval. So before proceeding ahead, let me set up a couple of notation for our convenience. So for any real valued sequence xn, and for any subinterval I of the unit interval, the AIN, which is the cardinality of n less than equal to n, so that the xn belongs to I. So with this notation, we say a sequence xn is equidistributed in the unit interval. Many people call it also uniform distribution. If for any subinterval I, limit n tends to infinity AIN upon n, so this AIN is some counting happening, and that we'll keep in mind. On the right hand side, the length of the interval b minus a. This is precisely the length of the interval I. And what is AIN? We are counting the number of elements of the sequence xn which are less than capital N in index such that xn belongs to I. In other words, to that counting thing, because counting is a hard thing, we all know. So what we do, we'll rewrite the definition that the numerator, what we are counting, can be written as the sum chi of xn, where chi is our characteristic function. So basically, in order to show something equidistributed, we had to count this AIN, this number of n such that xn belongs to I. Rather than doing that, we'll write it in terms of the sum. And in other words, the definition can be rewritten as that a sequence xn is equidistributed if and only if, in the unit interval, if and only if the following limit over this characteristic function is precisely the integral of chi x, and this is precisely the length of the interval on the right hand side. Once we rewrite, the benefit of this is the whole calculus, basic calculus is in our disposal. Once we rephrase the definition, because earlier you want to show something is equidistributed, then you have to count that xn, how many xn are in that interval. But that's an extremely hard thing, we all know based on our experience. But the moment you bring in the characteristic function, now the whole calculus is in our disposal. This is one of the instance where you can see the power of rewriting in a bit different language. And because characteristic function, they are dense in the Riemann integrable function on a closed interval, in particular periodic Riemann integrable function, we can rewrite the definition of equidistribution as xn is equidistributed in an unit interval, if and only for any Riemann integrable function of period 1, the left-hand side limit should be equal to the integral of f of dx. So in particular, if you choose your f as an exponential function, what does this give? That if a sequence is xn is equidistributed, then necessarily, because this is a special case of this f, the left-hand side, the exponential sum should be 0. So just by rewriting the definition, we produced a necessary criterion. A sequence xn equidistributed or uniformly distributed, necessarily the exponential sum equal to 0. Right? So one of the natural question is, then what about the sufficient condition? If this is 0, is it necessarily is sequence is equidistributed? And this was answered by Hermann Weyl in 1916, where he investigated about the sequence n square theta. And in order to prove n square theta is equidistributed, he showed a sufficient condition of the equidistribution, what is nowadays known as Weyl criterion. And it says a sequence xn is equidistributed if and only if the exponential sum is equal to 0. So both the sides are true. And this is another very interesting paper in number theory in the same year where the Ramanujan's paper appeared. So basically, what is the take-home message from here? Whenever we see a sequence is equidistributed or not, in the background, there is some exponential sum is going on. That's the take-home message for this part. So in particular, if you look at the sequence n theta, where theta is irrational, basically we have to investigate this exponential sum, but this is just a GP, and that geometric progression can be written like this. But because theta is irrational, as n goes to infinity, this quantity goes to 0. Only a couple of lines. But if you look at the original paper of Bohl, I don't know, I have put the, if you look at this paper of Bohl, this is around 97 page paper, 90 plus paper. But the power of Weyl criterion, after we connected this to equidistribution and the exponential sum, this is just a couple of lines. And one of the very, so this is for the set sequence equidistribution, but we have to go to set equidistribution. Consider finite multisets n. What is multisets? Basically, let's say 3 appear more than 2 times. The number of times it appear will count that many times. That's a multiset. So a collection of multisets an with the restriction that cardinality of an goes to infinity as n goes to infinity set to be set equidistributed with respect to some probability measure mu if for any subinterval ab of 0 to of the unit interval, the cardinality of t in the set an such that t is in the interval divided by cardinality of an as limit n tends to goes to infinity should be integral of a to bt. This is generalization of the earlier definition we saw in not only in terms of set but also in terms of the measure. So earlier the length of the interval is precisely the Lebesgue measure of the interval. But now this is with respect to any probability measure. So in particular, if you choose your an as x1 x2 xn, you recover the sequence equidistribution. And in the set equidistribution, in this setting, in 1924 Wiener and 1929 Schoenberg, independently they showed a Weyl criterion kind of thing, which says a finite multisets or a sequence of finite multisets an are equidistributed with respect to some positive continuous measure, probability measure, if and only if, first of all, the Weyl limit should exist. What is the Weyl limit? This exponential sum. This sum on the left-hand side is appearing. The CM is known as the Weyl limit. That Weyl limit, first of all, should exist, and limit n tends to infinity to 1 upon n, the summation of CM square, that is this square should be equal to 0. So this is an if and only criterion, and this is kind of a generalization of what Weyl showed for sequences. So with this very brief introduction to equidistribution, so some of the more very famous result is we saw n theta, then n square theta, and by the way, in the 1916 paper of Weyl is a very interesting paper, because in order to show the n square theta is equidistributed, the method he adopt is what is known as a differencing method. So he has to come up with new techniques to estimate those kind of sums. In particular, if you choose any polynomial with one of the coefficient is irrational, again, that is going to be P of n theta is going to be equidistributed. That's Weyl result. But one of the very famous result in this topic is P theta, which is due to Vinogradov, where P is prime and theta is irrational. They are going to be equidistributed. But this is one of the very celebrated paper, and if you like to read more on this kind of thing, this is a great paper to start to read. So without going into much details, so in this topic, one of the very famous conjecture, if you look at the 3 by 2 and the fractional part of the sequence 3 by 2, and you look at the power of n, 3 by 2 whole to the power n, and you look at the fractional part of that, they are going to be equidistributed with respect to Lebesgue measure in the interval 0 to 1. Even dense is not known. So if you want to have fun with something, so this sequence is dense in the interval 0 to 1. That is itself is not known. It's a quite challenging problem. All right. So with this is a like very brief introduction what is equidistribution, and we just keep in mind that whenever we see something equidistribution on the background, there is the exponential sum is playing here. It's an if and only criteria. Studying equidistribution is same as studying exponential sum. That's why it has the connection with the analytic number theory. So in order to introduce what is Sato-Tate conjecture, let me introduce very briefly elliptic curves. So elliptic curves are mainly cubic equation. An elliptic curve over any field means we can take this ABC belongs to the field. In particular, elliptic curve over Q, by taking the LCM, we can say, an elliptic curve is a cubic equation which do not have any repeated roots. In particular, these are examples of two elliptic curves and their graphs. So what is the interesting thing about elliptic curve? They have there is a group structure inside it. So if you how do we define a binary operation? So now choose 2 points, let's say P1 and P2, and you draw a straight line, and you look at the third point where the straight line intersect, and you just take the reflection of that. And that we define this binary operation plus HP1 plus P2. And with a little bit more that with the addition of the point at infinity, assuming point at infinity, I'm not going to say much about it, but with the notion of point at infinity and with that operation, the points of elliptic curve has a group structure in it. In fact, this example of elliptic curve is one. This is one of the motivation to define the definition of group H in abstract sense, right? I mean so before the group, the way we read the definition, before that came, there were several instances where this kind of structures were being observed. So if you look at the work of Euler around 1729 and Bernoulli and all, so this was already observed. This is one of the instance or example where such structures were being already kind of observed. So for any field K, if you take an elliptic curve over K, what does it mean? Elliptic curve over K means the coefficient A and B belongs to K. And E of K basically collection of all the points on the elliptic curve, which each coordinates are on K. That's what our E of K. With the point at infinity, basically this is a subgroup of E. This was proved by Poincaré in 19th century. In particular, for example, if you choose your field as F37, which is a finite field, a field with 37 elements, and if you look at this curve, y square equal to x cube minus 5x plus 8, and if you count what is the group, which all the coordinates are sitting on F37, that is precisely Z3 direction Z50. And I mean, if you want to have fun with this, you can choose a finite field. You take a cubic equation, which don't have any repeated roots, and you try to figure out the group. It was really a fun things to do. So in general, how does this group look like? E of K. So collection of all the points on the elliptic curve where each coordinates are in K, how does it look like? And this is a famous result of model. There is no single answer. Of course, it depends on K, where in 1922, model proved that I mean, the group is abelian, that's pretty obvious. The way we have defined our operation, whether you add P1 with P2 or you add P2 with P1 doesn't matter because you are drawing a straight line, right? So this group is abelian, pretty obvious. We have, I mean, you already saw examples that that group need not be cyclic, but model in 1922, he proved that the group is finitely generated. Especially if you choose your field as Q, the group is going to be finitely generated over Q. So this is a very interesting thing, right? What does it say? Basically, you can have only finitely many points on the curves, which coordinates are rational, and joining that straight line, you can recover all other points which coordinates are rational. Amazing result, right? I mean, in both geometrically, algebraically, whatever way you would like to think, this is a very, very nice result. And because that is an abelian group, in other words, the group with all the coordinates are rational, which are on the curves, can be seen as the finite part, which is a torsion part of the group. And because this is abelian, we know this can be written as direct sum of cyclic groups plus some copies of Z. And the number of copies of Z is precisely known as the rank of elliptic curve. You might have heard about it. And this is the torsion part of it. So what about the points on elliptic curve who have integer coordinates? So that need not be a subgroup. And Jiggle in 1928 showed that the number of points on an elliptic curve, which both the coordinates integer, is a finite set. There are only finite number of such points. Then it's a very natural question. Someone can ask how many. So what is your upper bound? How many such points are there given an elliptic curve over Q? And that was precisely conjectured by Artin in his PhD thesis, and later on proved by Hasse, that if you take an elliptic curve over a finite field, P, and if you look at the number of points who have on the curve, which coordinates are on the finite field, minus P minus 1, this cardinality should be less than 2 square root of P. This was conjectured by Artin in his thesis and later on proved by Hasse. And this is what is known as Hasse principle or Hasse bound. Then one of the very natural question is how the rational points, what is the rational points? Basically those points on elliptic curve whose coordinates are in Q. Given elliptic curve over Q, how the rational points are distributed. So before going there, let me set up a few more notations. So given an elliptic curve E over a finite field, we call trace of E, or trace of the Frobenius is P to the power R plus 1 minus the number of points of elliptic curve whose coordinates are on the field. That is what trace of Frobenius or trace of E. And in 1950, Seto, based on numerical evidence, and 1951 Tate, based on theoretical evidence, they conjectured that if you take an elliptic curve, our Q, which does not have complex multiplication, then the trace of Frobenius or the normalized trace of Frobenius are going to be equidistributed in the interval -1 to 1 with respect to the measure, semicircular measure or Seto-Tate measure. In other words, what they are predicting, if you plot a graph of the trace of Frobenius of the, let's say this elliptic curve y square equal to x cube plus x plus 1, and if you look at the trace of Frobenius P, then the trace of Frobenius is going to be equidistributed with respect to the semicircular law, or what we call is H, Seto-Tate law. And this is what is known as the Seto-Tate conjecture, and this is now a theorem due to Taylor, Harris, Shepard-Barron, Gerard, Klogel, and Bernard-Lai. And this is one of the major development, I would say, in a recent past. So for today's talk, I'm not going to talk much on this setting, but we'll shift ourselves in the finite field setting particularly. After the conjecture, one of the major development was due to Birch, and he restricted to elliptic curve over the finite field AP, and he showed that the trace of Frobenius our finite field of elliptic curves as P varies are going to be equidistributed in the interval -2 to 2 with respect to the Seto-Tate measure or semicircular measure. So what is showed in more explicitly to prove his result, he used the mighty method of moments. So he obtained all the moments, and he showed the moment match with the moments of the semicircular distribution, and as a result, the trace of Frobenius obey the Seto-Tate law or the semicircular distribution. More explicitly, he showed this sum is our all elliptic curves over the finite field, and the even moment he is obtaining for the trace of Frobenius, or the CK is the Catalan number. What is a Catalan number? Catalan number is precisely you take an polygon, n polygon, and you draw a line, and you count number of triangles which does not intersect each other. And there is a whole book. There are hundreds of definitions of Catalan number. It appears very naturally in nature. So the even moment of the trace of Frobenius is the Catalan number. The odd moment is very easily you can show using the symmetricity 0. And these are precisely the moment of the semicircular distribution, hence the trace of Frobenius over the Seto-Tate law. So in case rest of the talk you do not find interesting or anything, this whatever appearing itself is very interesting. So what is happening on the left hand side? We are dealing with trace of Frobenius, which is more of a geometrical, right? Elliptic curve or genus 1 curve, right? And then on the right hand side, the Catalan number is appearing. It is a very combinatorial object. It is in nature or in many places this Dutch appear, right? And the even moment is precise. Even moment of the trace of Frobenius is precisely the Catalan number. By its own right, this is itself is like super interesting, at least for me. And once Barth proved this, then that was immediately extended by Kalch and Sarnak, famously known as the Cash-Sarnak theory. Yoshida, Delin, Brook Grenville, Baer, Zhao, Banks, Parlinsky, and many more. I mean, huge number of literature available. In case any name I haven't mentioned, I apologize, but there is literally a huge number of literature available on this topic. But what we were interested.
Sudhir, could I interrupt
Yes.
you? Sorry. What is the difference with the satotate? I mean, you're summing over all possible elliptic curves. Is that the difference?
Yeah. So basically, the satotate was elliptic curve over Q. And there you taking the reduction mod P and doing, and this is directly the elliptic curve over finite field. And this is something known as a bit vertical setting.
I see. And we are making a summation over E as in
yeah, these are all elliptic curve. Once you fixed a finite field, you are looking all the elliptic curves over that finite field, and then you are looking the trace of Frobenius and their moment we are taking.
So it's a finite sum. Huh? It's a finite sum.
Yeah, then we are changing the field.
Then we are changing.
Yeah,
Okay.
so what it's a frame, you collect all those elliptic curves, you look at so it's like you make a bucket, you fix a frame, you look at all the elliptic curves and collect the trace of Frobenius of those elliptic curves. You put on the bucket and then you change prime. Then again you have bunch of trace of Frobenius, and then you are looking at the distribution and they obey the semicircular distribution. That's what this is.
Thank you.
Yeah. The original conjecture is much harder because those are elliptic curve over Q. But what we were interested in, looking elliptic curves which trace of Frobenius are in arithmetic progression. So not just we will collect those elliptic curves which trace of Frobenius obey certain congruent condition, and that for any m and n we denote this EMM p to the power r. This is the finite field over f p to the power r. This m is this, and this capital M is more. And in order to understand the distribution of trace of Frobenius with this restriction or with the congruent conditions, we denote S K kappa MM p to the power r is the collection of. I mean, basically, we have to study the moments of the elliptic curves, what Barth did, but now with the restriction. So now we'll sum over those elliptic curves so that the trace of Frobenius is congruent to M mod N. And we have to, this normalization is very naturally, we have to normalize it. Basically, we have to obtain all the moments, both even moment and odd moment, in order to study the distribution. And we showed in a joint work with Catherine and Ben that even after this restriction, the trace of Frobenius of elliptic curve over finite field is going to be equidistributed with respect to the same semicircular measure, but with a weighted version, because the normalization we have done that is going to show up. But that's not so bad, that's very natural. So what does it is saying that because once you put this restriction, this is even very strong condition, right? Lot of elliptic curve is going to be thrown out, but the set which will become very thin. But even after this restriction, the trace of Frobenius are going to obey the satotate law, the weighted satotate law or the weighted semicircular distribution. To prove this, we have to obtain both the even moment and odd moment. But in this case, obtaining the moment are going to be a bit more challenging. That we showed that the even moment of the trace of Frobenius, this is in the denominator we have the zeroth moment. We are dividing the even moment by the zeroth moment. The even moment is again going to be the Catalan number. H r tends to infinity. What is so we have the finite field f p to the power r. If you fix a prime, And if you go on the tower like P square, Fp cube, so the and the often the even moment is going to be the main term is going to be the Catalan number. This is the error term. So then we can make very interesting statement about the error term or the rate of convergence. But for today's talk, we will restrict ourselves just to the main term. Not only varying R, if you vary the prime, earlier in what Birch was doing, in his case R was fixed, R equal to 1. If you vary the prime, still the even moment with the restriction of arithmetic progression, still the main term is going to be Catalan number. And we can take a hybrid statement so that P plus R goes to infinity, still the main term is going to be the Catalan number. So as I say, if you choose your capital M equal to 1, this precisely recover the Birch result, because for him the odd moment was 0, that is pretty natural, just using the symmetricity, and even moment is Catalan number, that's why he obtained, or from here also we can. So Castrick and Hubris, they also had looked at the trace of Frobenius congruent to T mod N. And for M equal to 2, this was studied by Kaplan and Petro. So they, in one of their paper, they had some application of this thing in the coding theory. So this thing does have application in coding theory and possibly in cryptography as well. So more than, if you look at the elliptic curve, who have a m torsion point. In other words, if there exists a point whose order divide m, we call that m, and we call that elliptic curve with an m torsion point. So if you restrict yourself for those curves who has an m torsion point and whose order of p equal to m, and again if you evaluate the moment, so again the even moment is going to be Catalan. So these are like very, very thin set, but still the even moment is Catalan number. Whether we can vary p goes to infinity, or we can vary r goes to infinity. Either way, the even moment are going to be the Catalan numbers. So how do we study the moments of this? So how much time? Yeah, okay. So how do we study the moments of elliptic curve? To study, we have to go to the Hurwitz class number. What is Hurwitz class number? So my small h is a classical class number of an imaginary quadratic field, and h of n is a weighted sum of the classical class number. With this sum, with a little restriction, d square divide n, so that n by d square congruent to 0 or 1 or 4, and I have little restriction on the SW is small as d of by 3 if d is minus 0, and this SD, in this case, imaginary quadratic, the class number of the imaginary quadratic field, in other words, the negative discriminant, but I have just for convenience, we are writing just h of d. And to study, we have to look at the generating function of the Hurwitz class number. And one of the famous result of Jaeger that he proved in 1976 says that if you look at the generating function of the Hurwitz class number, so this is the generating function of the Hurwitz class, this capital H is our Hurwitz class number. This generating function is going to be a Mach modular form of weight 3 by 2. But in our setting, because we are interested in the arithmetic progression, in our setting, we have to study the generating function of the Hurwitz class number and the moment of, not just generating, we have the moment of the generating function of the Hurwitz class number with the restriction such that t congruent to n mod n. With this congruent condition, we have to analyze the generating function of Hurwitz class number. And in literature, this has been studied before. For capital MH1, kappa equal to 0, and if you restrict your NHP, this is the famous, one of the famous result of Hler is h of 0, 1 of p equal to 2p. Right? So yeah, before, I should make a remark that studying this kind of thing, the moment of the moment of the trace of Frobenius can be done. One of the major tools they used is the trace formula, Euler-Selberg trace formula, Selberg trace formula. Someone can use sheaf theory. Someone can use elliptic representation and because we put this restriction. For example, the result of Birch, he used trace formula, and most of the result exist. The Dutch use the Euler-Selberg trace formula. In our case, we have to use the Mach-Modeler form or something known as harmonic mass form, and that is the reason we are bringing Mach-Modeler form, because the result of the J-gear. So, and then we saw that the even moment of the Hurwitz class number divided by the zeroth moment, and the main term is precisely again the Catalan number as n goes to infinity. And how do you go from the even moment to odd moment? Even moment of the Hurwitz class number to the trace of Frobenius. This is mainly due to during there is a connection of the trace of Frobenius and Hurwitz class number, but the way in the slide it is appearing mainly due to scoop. But originally this connection was found in the famous paper of during in 1974. So if my script E p to the power RT is collection of those elliptic curves such that trace of E equal to T, and if NAPR of T, this is precisely summing over E, so 1 by the number of automorphism of E over the finite field, then 2NA of P to the power RT can be written as, basically these are this sum, right? Can be written as precisely in terms of the Hurwitz class number. And using this connection, if we can prove the even moment of the Hurwitz class number, we can go back to the even moment of the trace of the Frobenius. It requires some more work, but nevertheless, because we have this connection, we can go back from one to other. So before proceeding, let me give a brief sketch of the proof. How do we obtain the even moment? Because the odd moment also in a similar fashion we can obtain. Even moment of the Hurwitz class number. So let my GKMM of n is the sum on T so that T satisfies the congruent condition. P2k of Tn, this is precisely the 2k Fourier coefficient of the Taylor series expansion of this polynomial, reciprocal of the polynomial. And with this notation, we have to show that the even moment of the Hurwitz class number with that congruent condition can be written as this GKMM, this G, minus, this is some sort of a recurrence kind of relation, because here in terms of smaller index, the smaller moment we can write down, but here the GKMM will. To prove this, we can use the induction hypothesis for kappa equal to 0, that's EG. And assuming the induction hypothesis, the proof is actually quite a bit complicated, but I'm just trying to give a very, very brief sketch. So assuming the induction hypothesis, the even moment, we can show that this quantity plus whatever we want, the main term is precise. This is the 0th moment of the Hurwitz class number, and the rate of convergence is n to the power k plus half plus epsilon. So if you can show that using induction, then the remaining thing was to show that in order to conclude that this is the main term, we have to show this can be absorbed by the error term. In other words, this quantity should be less than n to the power k plus half plus epsilon. So next, we would like to show that this quantity actually can be absorbed by the error term. And to do that, we have to look at the Rankine-Cohen bracket of the generating function of the Hurwitz class number with theta operator. And this idea is mainly due to Mikhail, where he's trying to prove a conjecture by Cohen. So as I say, most of the literature in this topic use the Echelon-Shelburne trace formula, and Jaeger gave a proof of the Echelon-Shelburne trace formula using harmonic mass form, or in other words, looking at this kind of thing, and that was used by Michael to prove certain conjecture of Cohen. So somehow in background, we are not far from the trace formula. So what we have to show is the Rankine-Cohen bracket of the generating function of the Hurwitz class number with the theta operator. If we add with this quantity where lambda is basically generating function of the small lambda, and small lambda is this quantity, the summation minus s to the power L. And if you hit this quantity with the U operator, we should show this should be a holomorphic cost form of weight 2 plus 2k on the congruent subgroup gamma 0 4m square intersection gamma 1 m. And if kappa equal to 0, this is a quasi-modular form. In other words, basically what we have to show that this Rankine-Cohen bracket of generating function of the Hurwitz class number and the theta after hitting the U operator, basically the nth Fourier coefficient is precisely can be written in terms of the G. Once we have that, basically if you add this quantity with G, this is precisely the Fourier coefficient of a cost form of weight 2k plus 2. And once we have that using Delin bound, very easily we can show that this can be absorbed in the error term. And but in order to show this quantity, only this quantity can be absorbed in the error term, and less than this, we can use this bound on lambda. So the lambda is less than equal to n to the power half into lambda mmn, and which is less than equal to n to the power plus epsilon. So combining everything, what we have concluded that gkmmn is precisely less than n to the power k plus half plus epsilon. In other words, the middle term that was appearing over here is actually the main term. This term with the Catalan number, what is appearing here is actually the main term, and that is why if you divide this term over here, so this is precisely the Catalan number. And now using the relation by scoop and during, we can go back to the even moment of the trace of Frobenius, and we can show the main term is basically the Catalan. So this is how we, I mean, I am putting a lot of things on the carpet, but nevertheless, this is a very, very brief sketch of how we can obtain on the even moment. So just to show the power of the method, my let nf n-1 is with the Gaussian hypergeometric function where a1 and aich and bj's are the characters. In particular, if you are interested we are interested in 2f1 and 3f2, and recently Ono, Ken Ono, Hassan Saft, and Nilam Saikia, they showed that if you look at the 2f1, the hypergeometric function, and if you vary the primes, they are going to be equidistributed with respect to the static measure. And the method being used are quite similar. And for 3f2, if you look at 3f2, and if you vary the prime, you look at lambda belongs to ft star, and if you vary the prime, they are going to be distributed what they are they call it something known as Batman distribution. So I'm going to come back to this, and but to conclude, in our setting, we have to, sorry, I'm going backward. We have to discuss the odd moment, because even moment, so far we have shown that the even moment of the trace of Frobenius with that congruent condition, the main term is the Catalan number. To show they obey the Setotate law, we have to show the odd moment is 0. And using very similar method, but it's a bit more technical, we showed the odd moment of the trace of Frobenius is precisely, the main term is precisely 0. As I say, there are very interesting thing we can say about this error term or the rate of convergence, but for today's talk, we strictly focus on the main term. So whether you vary R or you vary P, or you can have a hybrid statement that P plus R goes to infinity, the main term of the odd moment of the trace of Frobenius is 0. How can you obtain that? Again, going back to the odd moment of the Hurwitz class number. So we studied the odd moment of the genetic function of the Hurwitz class number, and we saw the main term of 0. And again, using the relations due to during and later on due to scoop, we can show that the main term is 0. So what we got, even after putting this congruent condition, the main term is the Catalan number of the even moment of the trace of Frobenius, and the odd moment of the trace of Frobenius is 0. And that is precisely the odd and even moment of the semicircular distribution. And in probability theory, we know a result if you the generating function of the moments, if they have a positive radius of convergence, then the distribution can be determined uniquely by the moment. And in this case, that happened. As a result, the trace of Frobenius are going to be equidistributed with respect to the semicircular measure with little bit of weight. This weightage there. But this is not so bad. So what is happening is, even after putting a lot of restriction on throwing away a lot of elliptic curves who do not obey the arithmetic progression or congruent condition, still they obey the Setotate law. That's what this is saying. And using this method, we recently give a very satisfactory answer for the bias conjecture, which is due to Miller in the finite field setting. So I'm not discussing this much, but nevertheless, the techniques being developed or being used to prove these results were very helpful to give a very satisfactory answer for the bias conjecture, but in the finite field setting. With Ken Ono, Hassan Saad, and Nilam Saikia, we restrict ourselves to Hessian elliptic curve, which are connected to again more certain hypergeometric functions, and we showed that again the distribution of trace of Frobenius, if you restrict yourself just to Hessian curve, again they obey the Setotate law. Similarly, the corresponding Gaussian hypergeometric functions also obey the Setotate law. Recently, we studied some algebraic surface with Nilam Saikia, and we saw similar phenomenon is happening. And also we with Nilam saw certain periodic hypergeometric functions. So what is happening? What I'm trying to show you is this phenomenon of Setotate. It is quite global. In many different settings, they obtain the Setotate law. So like Gaussian distribution is very natural, right? It occurs in nature like everywhere. Now, if you count, if you look at the heights, let's say in the state Odisha, the distribution is supposed to be Gaussian, and so forth, so on. In the same way, on this kind of if you look at the rational points of algebraic surfaces, again the Setotate phenomenon is occurring, and in the other side there is hypergeometric series. But in case of hypergeometric series like 3F2, what Ono, Hassan, and Saikia have shown, the distribution is not Setotate or not semicircular, of a different distribution, what they are calling pattern. So there are a lot of questions still to study and investigate what is happening, and what are the hypergeometric series who obey the Setotate law, and what are the class of hypergeometric series which does not obey saturated line. So that's the much more interesting in many ways, but nevertheless, right now very little understanding, at least I have. Maybe in future, someone else might study, give more better understanding. So with this, thanks a lot for listening patiently. Yeah, if you have any question,
Thanks a lot for that lovely talk. But it was pretty heavy in the end. Can you just slightly repeat? You were showing the final result that you obtained, and you had some comments to make. If you could repeat just those comments, like you said you were throwing out several elliptic curves. Of course, it's stuff you mentioned before, but if you could just repeat, it'll be fine. Like that weighted probability that you're calculating. Could you just repeat that?
yeah. So what we are looking at, basically, like earlier, maybe let me go back. So this theorem I mentioned earlier also. Yeah, basically what we are doing, we are looking those elliptic curves whose trace of Frobenius obey this, obeys this arithmetic progression or this congruent condition. So basically, in this case, you are fixing first the prime P, and you are collecting all those elliptic curve over FP whose trace of Frobenius obey the congruent condition.
Okay.
So now this become earlier, you see in our bucket, we collect all those trace of Frobenius for any elliptic curve over FP. Now in your bucket, you are collecting only those trace of Frobenius who obey only this congruent condition. This is a much thinner set.
Yeah. But you have weighted it with the
Yeah, this weight is very natural actually, because this has to do with the number of isomorphism classes. So, but still the interesting thing happening is still you have something like setotate, because this set supposed to be quite thin, that what Borch studied.
Okay. Makes more sense now. Thanks. If anyone else has any questions or comments. If not, we thank the speaker once again. Thank you, Sudhir.